Welcome back. Today we are covering the last branch of model layer, which is when to fine-tune. Many teams that reach for fine-tuning have not exhausted the cheaper options first. This is not a criticism, it's just a pattern. If a model gives suboptimal output, the team may decide to fine-tune because it improves the model quality. They spend few weeks preparing a dataset, run a fine-tuning job and get marginal improvement. Then they discover that rewriting the system prompt would have solved the problem in an afternoon. The decision to fine-tune should come after you have answered specific questions about what prompt engineering and RAG can do and cannot do for your use case. This video gives you the decision framework. We are covering three things today. The first one is the distinction between prompt engineering, RAG, and fine-tuning as answers to different questions. The second one is a 4-question framework for deciding which tool applies to your situation. And the third one is the real cost of fine-tuning in GPU hours, dataset requirements, and operational overhead, so you have some real metrics and numbers before you committing to it. Prompt engineering, RAG, and fine-tuning are not three levels of the same solution. They solve different problems. Treating them as a complexity ladder, try prompting first, then RAG, then fine-tuning, leads to using wrong tool for the job. Here is what each one actually addresses. Prompt engineering changes how you communicate with the model. The model's knowledge and capabilities are fixed. You are changing the instructions, the context, the format, the example that you provide. It is the right tool when the model already has the knowledge and capability required for your task. Prompt engineering can solve some specific type of problems like output format problems, instruction following failures, or inconsistent structure. Basically, the problems that the model can do well, but it's not doing it because you have not communicated the requirement precisely enough. RAG changes what information the model has access to at query time. The model's weight are unchanged. You are injecting relevant context into the prompt at runtime, retrieved from a document store, a database, or an API. It is the right tool when the model needs information it was not trained on. Your internal product documentation, for example, or maybe account data, or maybe customer related information, any knowledge that post-dates the model's training cutoff or that is proprietary to your organization. RAG doesn't change how the model reasons, it changes what the model reasons about. Fine-tuning, this changes the model's weights. You are modifying the parameters of the model itself by training it further on the dataset you provide. It is the right tool when you need to change how the model behaves, like its style, its tone, its domain-specific vocabulary, or its output structure, in ways that cannot be achieved through the instructions or retrieved context. Fine-tuning is not about giving the model new information. A fine-tuned model doesn't know more facts than the base model, but it just behaves differently. That distinction, information versus behavior, is the key to decision framework. If your problem is that the model lacks information, fine-tuning will not fix it. If your problem is that the model behaves incorrectly for your domain, fine-tuning may be the right tool once you have ruled out the cheaper alternatives. Okay, let's jump to the decision framework. There are 4 questions in order. The first one that gives you a clear answer is your stopping point. Question 1, is this prompt engineering problem? Ask specifically, does the model have capability to do what I need, but is applying it incorrectly? Let's take a look at some examples. The first one is a legal contract review agent that summarizes contracts in plain English, but keeps using legal jargon the client doesn't understand. The model can write plain English, it does it everywhere else. It's not doing it because the instruction is not specific enough. That is a prompt engineering problem. Adding an explicit instruction like respond in plain English, avoid legal terminology, define any technical term you use, then you test and measure it. Another example is that a customer support agent that answers in the correct language but gives inconsistent answer lengths. Sometimes 1 sentence, sometimes 5 paragraphs. The model can control output length. It's not doing it consistently because the constraint is not in the prompt. Add a length instruction and then test it. So basically the test for a prompt engineering problem is that can you write a prompt instruction that if followed precisely would produce the output you want? If yes, it is a prompt engineering problem. Fix the prompt before considering anything else. Question 2. Is this an information problem? Ask specifically, does the model give incorrect or incomplete answers because it lacks access to specific information? Let's look at some of these examples. A product support agent that gives outdated answers because the model was trained before your last 3 product releases. The model is not reasoning incorrectly. It doesn't have the information. RAG is the right tool. Ingest your product documentation into a vector store. Retrieve relevant chunks at query time. The model now reasons correctly from current information. Another example is that an internal HR agent that cannot answer questions about your company's specific leave policies because those policies are not public information. The model was not trained on those policies, so RAG is the right tool for that too. Fine-tuning will not solve an information problem. So the test for information problem is asking this question, that would giving the model correct information in prompt produce the right answer? If yes, it is a RAG problem, not a fine-tuning problem. Okay, let's move to the next question, which is question 3. Is this a behavior problem that prompt engineering cannot fix? This is where fine-tuning becomes a legitimate consideration. Behavior problems that resist prompt engineering typically fall into 3 categories. The first one is a domain-specific output style. For example, a medical documentation agent that needs to produce clinical notes in a specific structured format, for example, SOAP note structure or specific terminology conventions with perfect consistency across thousands of documents, you can prompt for this. At scale, a base model will drift from the required format. A fine-tuned model trained on thousands of correctly formatted clinical notes will produce that format consistently without extensive prompting. Latency and cost from long system prompts. If your system prompt is about 2000 tokens of detailed instructions to get the model to behave correctly, fine-tuning can bake that behavior into the weights and reduce your prompt to about maybe 200 tokens. The model behaves the same way. Your input token cost drops by 90% on every call. At high volume, that is legitimate cost engineering argument for fine-tuning. The third category is specialized domain vocabulary and reasoning patterns. A cybersecurity agent that needs to reason about CVEs, exploit chains, and vulnerability severity in a way that a senior security engineer would do, not in a way that a journalist LLM discusses security. A fine-tuned model trained on security incident reports, CVE analysis, and penetration testing documentation reasons differently about these topics than a base model with a security-focused system prompt. So this is a fine-tuning candidate. Let's move to next question. Question 4. Have you measured what prompt engineering and RAG actually achieve before deciding they are insufficient? Before committing to fine-tuning, define a specific quality metric for your task. Accuracy on a test set, human evaluation score on a sample of outputs, hallucination rate, whatever is appropriate for your use case. Measure your current prompt against that metric, then measure an improved prompt against it, then measure RAG against if it is applicable. If you cannot define a quality metric for your task, you are not ready to evaluate whether fine-tuning works either. Fine-tuning without an evaluation framework is an expensive guess. Okay, so if you have worked through the framework and concluded that fine-tuning is the right tool, the next decision is which type of fine-tuning. Full fine-tuning updates every parameter in the model. All weights are modified during training. This requires a significant GPU memory, enough to hold the model weights, the gradients, and the optimizer state simultaneously. There are other fine-tuning techniques like LoRA, which stands for low rank adaptation, and it's the parameter efficient alternative most teams should start with. Instead of updating all model parameters, LoRA freezes the original weights and trains a small set of additional weight matrices that are added to the frozen weights at the inference time. Then we have QLoRA, which takes LoRA further by quantizing the frozen base model weights to a 4-bit precision during training. This reduces the GPU memory requirement further. A 7 billion model can be fine-tuned with QLoRA on a single 24 GB GPU. The trade-off is slightly longer training time due to quantized overhead. I'm not going into too much detail on these fine-tuning techniques here because I have already covered them in a separate video on my YouTube channel. In that video, I break down LoRA versus PEFT versus full fine-tuning and explain when to use each. So if you want a deeper understanding, I would recommend checking that out. The link can be found in the description. Let's see what fine-tuning actually costs. Cost is where most fine-tuning decisions become more concrete. Let me give you real numbers across the main approaches. Dataset preparation is the cost most teams underestimate. Fine-tuning requires a dataset of input-output pairs that demonstrate the behavior you want. For a domain-style adaptation task, say clinical note formatting, you need a minimum of several hundred high-quality examples to see meaningful improvement and several thousand for robust results. If the examples need to be created or labeled by domain experts, you need to involve a medical professional reviewing those clinical notes and then a security engineer validating CVE analysis. That labor cost is frequently larger than the compute cost. A dataset of 1000 expert validated examples at 2 minutes per example is 33 hours of expert time. At any reasonable consulting rate, that is significantly higher cost that doesn't appear in GPU billing. Then comes your compute cost. Compute cost for training run itself depends on the approach you take for fine-tuning. OpenAI fine-tuning API is the simplest operational path. You provide a JSON-L dataset, submit a fine-tuning job, and OpenAI trains and hosts the model. Current pricing for GPU 4o mini fine-tuning is approximately $3 per million training tokens. A dataset of 1000 examples at 1000 tokens each is 1 million tokens, roughly $3 for the training run. Per token inference on the fine-tuned model is higher than the base model, approximately double. Even though it's operationally simple and you are not standing up any infrastructure or there is nothing to manage, you have limited control over the training parameters. Or if you decide to go with self-managed fine-tuning on a cloud-based GPU instance, for example on AWS or Azure, you will typically be charged on an hourly basis for the GPU resources. On top of that, you will also need to account for ongoing inference cost once your model is deployed. The crossover point between OpenAI fine-tuning API and self-managed depends on your inference volume and whether you already have infrastructure. At low volume, the OpenAI API is operationally simpler and cheaper in total cost, including engineering time. At high volume with existing GPU infrastructure, self-managed fine-tuning on an open source model is cheaper. A fine-tuned model is not a one-time cost. When the base model updates, your fine-tuned adapter may need to be retrained. When your data distribution shifts, new products, new technology, and new output requirements, the fine-tuned behavior may drift from what you need. Fine-tuning introduces a maintenance obligation that prompting and RAG do not. So prompt engineering has no maintenance cost when the base model updates. RAG has a data freshness cost, but no retraining cost. Fine-tuning has both. Let's wrap it up. There are 3 takeaways from this video. The first one is that the decision order matters. You should always examine prompt engineering first because it's the cheapest option and solves more problems than you might think. RAG is second. If the problem is information access, fine-tuning will not fix it. RAG will. Fine-tuning is third option only after you have measured what the first to achieve and confirmed that they are insufficient for your specific quality requirements. Second takeaway is that fine-tuning changes behavior, not knowledge. If you need the model to know something it doesn't know, that is a RAG problem. If you need the model to behave differently than it does by default, that is a fine-tuning candidate after ruling out prompt engineering. The third one is the ongoing cost. A fine-tuned model introduces a maintenance obligation. Dataset curation, retraining when the base model updates, and monitoring for behavioral drift. So you need to factor that into your decision before you start. We are closing this layer with 3 questions and 3 decisions. Which model? Where does the inference run? When does the base model need to be customized? Next is layer 4, which is memory and knowledge. We will cover that in the next video. If you like this video, please consider subscribing to the channel. I'll see you in the next one.